Well, good morning. We have already covered all material which is required from you in this course. In the book you have, I think, 2 more chapters about modern physics, which actually implicates that explicitly that whatever we learned is wrong. I mean, it isn't really wrong. But we have to recognize that whatever we learned is a certain approximation of nature, and we have to be aware of how approximate it is. Even, I mean, if you read over there, you will find out that even Newton's law, F equals ma, is not valid. Because probably some of you heard that we cannot exceed speed of light. Well, so it means that if we apply a constant force, there we cannot accelerate at a constant rate, because then we would have to exceed speed of light. So, but this is not the subject of this course. And what I was thinking of doing today is to juggle the material which we learned. Because this is how you will have to do, and what you will have to do with the knowledge which you acquired over here in other classes. You will have to be able now to immediately to associate various physical quantities. You will have to immediately to recognize applicability of various relationships. And from that you can predict whatever will happen in the system in which you will become specialists. It doesn't matter if it is going to be a chip, or if it is going to be a helicopter, or it is going to be a building. You will have to be able to analyze it. So how about what I will do now is I will bring up various relationships, and we will have to recognize it, because I mean I want now to make a review. Today I'm going to do review of the material which is which we covered this semester, so it is going to be relevant to your final test. All right. I mean, one thing about physics is that you cannot forget what was before. So I will also bring up some general relationships from Physics 1, and well, we'll have to be able to recognize how it relates to this what we discuss in this chapter. All right. So, and you can even help me now to do it. Now I want to write a lot of formulas which contain symbol F, capital F, and then we will have to discuss what is it for. All right. So how about if I write F equals ma, F equals K Q1 Q2 over R squared times R. F equals QV times B. What else did we know for F? Can you remind me some formulas, some other formulas? If not, I'll find. Oh, yeah, I have more here. Oh, and even in a different form. How about if I write it in a differential form? dF equals I ds cross product B. We also, I mean, this one is not that important. However, we had it. IL cross B. Oh, and how about if we write actually now symbols which look like that. mu0 I1 I2 over 2 pi A times L, and F equals QVB. No, that's enough. So, can we find, in these equations, can we find the one which says what is a force? Yeah, because in all those equations, F represents force. Now, when a question is what is something, it means that it's the definition. Which of those equations defines force? Anybody has a suggestion? First one. If you recognize the first one, who agrees that the first one is the one which defines the force? Actually, it isn't the one. However, it was a good bet, because this one is the most general formula which was applicable throughout two courses. Force is a primitive concept. It describes, we don't have really a formula which defines force. Now, if you wanted, because Newton's second law is an axiom, and before we understand, not a definition. It's an axiom. It does not define force. And by the way, more contemporary version of Newton's second law, the one which actually is applicable also in the next chapter in modern physics. Do you remember that version of Newton's second law? It related momentum of a particle with force, so that the force exerted on the particle is equal to the rate of change in momentum. All right, now how about if we go through these equations and now identify when the formula is applicable and what actually F stands for. So let's start with the first one. What is F over here, and how this F is different from all the other F's? Any suggestions? Jerry? This is force exerted. This is force exerted on a particle. You mean a force or the force? A force. Who agrees that this is a force? Vincent, do you agree? Brian? No, and Brian is right. It's not a force. It's the force. Obviously, it's not the force with the Jedis use. Which force is this, Brian? The sum of all forces, correct. This F stands for the net force exerted on the particle or the net force exerted on the object, whatever we discussed. All right, so how this F is related to this F, for example? Can these two be equal? Under what circumstances these two could be equal? Well, first, let's recognize what is that, what this F stands for. Anybody? Adam, yes?
The force from one particle Q1 on the...
Now, I hate that you say that the particle is Q1. I prefer that you say from particle 1, and forces are not exerted from, but by. So Adam wanted to say that this is the force exerted by particle 1 on particle 2. Now Q1 and Q2 stand for charges of the two particles. All right, but let's concentrate now about F. What is F? It is a force which describes particular interaction between particles. Yeah, what interaction? Christy? Yeah, do we interact that way? Anybody? I mean, do you interact that way with your neighbor? Do you? Adam says yes. Mike? Yeah. Yes, okay. I buy that. How strong is that interaction between you? Yes, Sam? Small, very small. Why? You are right, actually. So actually, the question was such that no matter if you said yes or no, you would be right. I would accept the answer. Yeah, because one is that indeed, whenever we have two particles, we can suspect this type of interaction. However, Sam, why is it small? Yeah. Because what? Well, electrons are even smaller. Yes, Robert. Yes, we are not particularly charged. Our charge, we are almost neutral objects. Practically, we are neutral objects. Most of the time, we are neutral objects. And so even if we consider ourselves to be particles, these two quantities, the charges of people are zero. So force is going to be zero. This force is actually strong somewhere else. Where? Let's say in an atom. Let's consider a hydrogen atom. Interaction between nucleus and electron orbiting that nucleus results from this interaction. What do we call this interaction, by the way? Mike? Anybody? We have to juggle it. We are juggling it today. Robert. Electrostatic. Good. It's what I'm saying. I meant Jerry. Yeah. How about that one? What's this one? I think Brian can say that. Vincent? What? I mean, I'm not juggling it sufficiently fast. We have to juggle it faster. Kyle, you can juggle it. Magnetic force, correct. So this happens when a particle travels through magnetic field, which is the region in which this particular force is exerted. Now, can these two be, well, how about that? Can these two be equal? Brian says yes, and he is right. Under what circumstances these two are equal? When the particle only travels through an electric field. Actually, we have to recognize also that they will be approximately equal. Now, because think about a situation in which we can actually say that they are. When would we say that they are equal? Give me an example of a situation when these two are equal. Obviously, you cannot take Jerzy and consider that right now the electrostatic force is equal to the net force exerted on Jerzy. Right? Why? Because we can recognize much stronger forces exerted on Jerzy. Which ones? Gravitational force. Which else? Jerzy. A force exerted by the floor or by the seat. Right, the normal force. So these are much stronger than any electrostatic interaction. So under what circumstances actually these two could be equal? Yeah, because as Brian said, this is the sum of all forces exerted on the object. And among all of those forces, this one can exist. So give me a situation in which actually I can say that only electrostatic interaction. Electron traveling through, produced by what? Proton, for example, yeah. So in a hydrogen atom, we can say that the net force is equal to electrostatic force. Now, how about an experiment which I made, a demonstration which I have shown you? And actually, this is also, well, one of the devices used in electronic labs. So all of you who are going to be electrical engineers, most likely you will use this device. I'm talking about an oscilloscope. Yeah, what do you use to deflect the electron beam in the oscilloscope? Not current. We create potential difference between what? Correct. Two plates, between two plates. Yeah, so in a capacitor, in an empty capacitor, although this is not called capacitor because capacitor is supposed to be an electrical element. But the two plates indeed behave like a capacitor, and they will deflect. Correct. Now, how about these two? When these two can be equal? I mean, this right. I mean, to be the same, yeah, because when an electron travels through a capacitor, this one is the same force as this one. Now my question is when this one is the same force as this one, because equal, it's again, what do we understand by equal? I wanted to say the same. When one becomes the other. Because we can have a situation that that this electrostatic force becomes the net force if the other interactions are insignificant. Because even in this oscilloscope, we say that only electrostatic force is exerted on it, but it's not true. Gravitational force is still exerted on it. However, a gravitational force is insignificant compared to electrostatic, so we can ignore that. All right, so when this one is the same force, not just equal, because by coincidence they can be equal for a moment. However, they will never become the same, because this one describes interaction, electrostatic interaction. This one describes magnetic interaction. All right, now what's we had two expressions for force, for magnetic force, this one and this one. Now when can I use this formula? Under what circumstances I can use this formula, and under what circumstances I can use this formula? When we are talking about differential segment, we can use which one? This one or that one? And where are the quantities which describe this differential segment? Actually, Adam is wrong. This force is a force exerted on a differential segment, so this is a fragment of an object. Right? Now, these two both actually represent what? Vincent, how about you? Oscar, sorry. A what? They are the same. They refer to the same thing. So when one formula is valid, the other is valid as well. What's the difference between these two formulas then? One refers to the magnitude and one refers to the force itself, to the force vector. Correct. Which one refers to the force vector? That one. Correct. And well, over here actually we have a case in which well, there is a major difference in the formula. I want to identify this major difference. What's the major difference in the two formulas? Multiplications. We use different multiplications because we multiply completely different quantities. Over here we multiply different quantities than over there. Yeah, let's take a look at symbol B. What is B here and what is B here? Christy, could you read that? B? Don't read B, obviously, but say what is B. B with arrow is good. Magnetic field vector. So B with arrow is the magnetic field vector, and B without arrow is the magnitude of this vector. Do not confuse, I know that you will still do it, but I beg you, in the future, do not confuse magnitude of a vector with a vector itself. What's the major difference between a vector and a number? Not the direction. They are combined differently. Operations of addition are different. Operations of multiplications are different. Like, for example, what kind of multiplication do we have here? Robert, how about you? Cross product. And what do we multiply in cross product? Vectors, and the result is a scalar, a number, correct. Since we got into products, so let's juggle, let's make a digression. And how many products do we know? 4 products. Ian, could you remind us the products? So, what do you mean scalar? Scalar product? Okay, scalar product. Let's and how about why don't you refresh our memory what we multiply and what we get in scalar product? No. In scalar product we multiply, Kyle? No. Vector and vector. What is a synonym to scalar product? Dot product. Correct. Dot product. All right. So now, in which product do we multiply 2 numbers? And then the name of that product is so trivial that you even don't know that don't remember that name. What multiplication? Of numbers, correct. So this is product of numbers. 2 times 3. In 2 times 3, we use product of numbers. We don't use dot product. Dot product is only used for vectors. We multiply 2 vectors and we get a number. Now, Ian, let's come back to this one. And what do we multiply and what do we get in the cross product? And the equivalent name for cross product is vector product. Good. And what do we multiply? What do we get? We multiply 2 vectors and we get a vector, correct. Teja, we are missing one product. What is the missing product? Yeah, we have product of 2 numbers and 2 products of vectors. A scalar product and vector product. Which one? Product of a number and a vector, and the result is going to be a... Do we have this product on the whiteboard? Quickly find it. We do. Which one? For example, first, here we have product of a number and a vector. Actually, in all of them, I mean, starting from here, in all of them we have product of a vector and a number. This is a number, this is a vector. Here we have a number and a vector. Number and a vector. Now, just one more thing to make sure that, because I remember that we were pretty confused about this, what ds is. What is ds? It's a segment vector. And what do we understand by segment vector? Then, right? Can you say what do we understand by segment vector? It's a vector which is aligned with the line itself. The segment. Yeah, we can say with the segment, because when do we have this segment vector? If we have a certain line, right, like piece of wire, we take a fragment of that line, which we call a segment. So this is a segment. All right. So it is aligned with the segment. We couldn't align it with the entire line because line can be curved, so it's a problem. All right, now, so which way should I align it? This way or that way? Which way? Well, in principle, it doesn't matter. And there are in formulas that this is very arbitrary. Now, in this formula, actually, we align it with the current, correct. So if current flows to the right, we will consider it to the right. If current flows to the left, we will consider it to the left. All right, so we know what is the orientation. How about the magnitude? The magnitude is supposed to be equal to the length of the segment. Correct. How about if I mark it that way? All right. Now I have a series of formulas. Oh, how about if we really jump? What epsilon stands for? Electromotive force, correct. And I brought up several formulas for electromotive force which we discussed. Now let's recognize what is what of what over here and when it is applicable. So I mean, what do they mean? Do we recognize this a relationship? Sam recognizes it as that electromotive force is opposite to a certain magnetic flux, right? Now, but do you know what is the name of the law? Anybody remembers the name of the law which relates magnetic flux with electromotive force? Yes, Oscar? It's one of the Maxwell's laws. Right, which one? Third one, right. Which say, I mean, and actually it has a name after a certain famous scientist. Yes, Owen? Faraday. Yes, it is Faraday's law of induction, correct. And well, in a trivial way or in a really abbreviated phrase, you can say that electromotive force is related to flux of magnetic flux. Now, when it is applicable, under what circumstances? What do we have to have? Actually, we could also recognize, how about if I add a little bit more general form and put n over here. When it is true. And what is what over here? Taya, can you quickly say that? N is the number of loops of what? For example, in a solenoid, correct? Yes. So this formula is. Oh yeah. So Owen actually said this was not one of Maxwell's equations. We will come back then to more general formula. Recall. Maxwell's one of the Faraday's law. All right, so N stands for for the number of loops. How about epsilon? Right now I'm trying to compare epsilons. What is epsilon in this formula? Which one? Correct. It is electromotive force induced in that solenoid. And it is related to what flux? It's related to magnetic flux. What magnetic flux? Because if there is magnetic field, I can find an infinite number of fluxes. If somewhere is magnetic field, and it has to be, this magnetic flux has to be a specific one. Yes. What do you mean? Yeah, you are right. I know that Oscar is right. He says inside of the solenoid. So it is the flux through a cross-sectional surface of the solenoid. Remember that flux is always associated with the surface. I change the surface and I have new flux. You have to relate it. I mean, if, in the original version, if n was equal 1, so it was electromotive forces just in one loop. And then we will have to consider surface spanned by that loop. Now, what was Faraday's law of induction as the third Maxwell's equation? It didn't have electromotive force here, but as I will write down also. And actually, I don't think that. This was equation. What was the difference now between the left-hand side, this one and this one? What was the difference? I mean, which one is more general, this one or that one? This one is more general. Yeah, where is the difference? Yes, yes. More general, it means that it is applicable to more situations. So that one was. And Taya actually already said to what it is restricted. It is restricted to loops. Now, what loops? Conductive loops. We had to make a conductive loop. How about that one? Kyle, what loop did we have over here? Could we have a piece of wire in that loop on the left-hand side?
Yes.
Yes, correct. Could we have some other loop on the right-hand side? Yes, correct. What loop? But a closed loop of what? Made of what? Because on the left-hand side we had to have a loop of a wire, of a conductor. And over here we don't. A what? Which is what? Yeah. And anything in which electric field can be produced. So, for example, a vacuum. We can have vacuum over here. We can't have it here. Yeah, over here we can just imagine an abstract closed loop, a geometrical object. Abstract object, not a material object. We just can imagine a line. All right. Now, how about this one? What was this about? And can this one be equal to this one? I mean, to be the same? What say? This one is for an inductor. Right, this one is for an inductor. Electromotive force producing an inductor. How about this one? Solenoid. So do they overlap or not? In other words, is a solenoid always an inductor, or at least behaves like an inductor? If yes, then we could say yes. But that it is the same quantity. That could be these would be the same epsilons. If we find a situation that an inductor is that a solenoid does not behave like an inductor, then in this situation the two in general the two epsilons are not the same thing. So is every solenoid? Well, actually I can ask two questions. Is every solenoid an inductor? And does every solenoid behave like an inductor? These are two different questions. And actually the answers are also different. Consult with each other. Coach, what's your opinion?
No to the first one, yes to the second.
And I forgot what is the first one. But the indeed answers were no and yes. No to which one?
Every solenoid is an inductor.
Correct. Every solenoid is an inductor. It's not true. And yes to the second one, which means that every solenoid behaves like an inductor. All right, now, so what's the difference between a solenoid and an inductor? Diego, what's your opinion? Inductor is a so is solenoid, but describe more precisely. It's an element, but what element? Inductor is an element which we use in an where? Electrical circuit. Yeah, it is used in an electrical circuit, in electronics, in TV. And it is a device which relates potential difference with current in a particular way. This is the way, because the only potential difference which exists across a solenoid is no solenoid. Inductor results from this electromotive force induced in the inductor. How about solenoid? Can we find a solenoid which is not an inductor? And on a junkyard, for example, we have them. Robert, do you recall them? Or Jeff? Jerry? You don't? Anybody work at the junkyard? Or from movies. I mean, what's the movie? James Bond, James Bond with Count Connery. I recall that there was a junkyard where they were crashing cars. And how did they move those cars? They were picking up with some kind of disc, right? What was that disc? A what? No, it was not a magnet. Electromagnet. Correct, it was an electromagnet. And what is an electromagnet? How is it made? Yeah, it's a coil. Yeah, but I mean, a coil which conducts current is called a solenoid. Correct. It's called a solenoid. Yeah, so we had a solenoid over there, right? And that solenoid, is that solenoid an inductor? It can behave like an inductor. It will behave like an inductor, but obviously it's not an inductor. I mean, can you imagine how big electronic devices would be if we use this type of solenoids? I mean, we could use it in TV, indeed, instead of those tiny ones. It has certain inductance. We would have to appropriately adjust capacitance still to make a resonant circuit. But a resonant circuit with that electromagnet, I mean, will make our TV, I mean, you will have to have electronics in the neighboring room to watch TV. All right, now this one is not that important, but do you recall what this one is for? Like V, what that V stands for? Kyle, do you remember? A what? Well, that one is like an aeroplane flying through the magnetic field of the Earth. So if we have, I mean, it's not an particularly important formula, but if we have a conductive element flying through a magnetic field, then electromotive force produced by that, yes, so like in an aeroplane, electromotive force between one produced by the wings, for example, will be related to magnetic field of vertical component of magnetic field produced by the Earth, wingspan, and speed of the aeroplane. Let's try something else. So how about if we try this? Actually, over here, maybe I will also write. What I stands for? Electric current, correct. Now, what's the difference between these two? And here I put a hint. And I want actually you to read it to each other. I mean, the right-hand side. So let's start with this. Is one of those equations maybe a definition of the current? The first one. Correct. The first one is a. Oh, this one. This one is a definition. Do we have another definition on the whiteboard? Yes. What's the other definition? No, the second one is not the definition. Which one, Owen? Third one. Third one is also definition. Now I'm getting confused. How is it that electric current has two definitions? Yes, yes, Oscar? I saw a bright light in your eyes for a moment. Brian, can you help? Well, yes, correct. Be more specific. Yeah, I mean, what do you mean by situation? Kyle, can you help? Thea, why we have two definitions of electric current? Because we have two different electric currents. Oh yeah, what? What are the two electric currents which we discussed? And actually these are the ones which exist. Not physical, we don't call it physical, but you are on the right track. One is associated, because what Adam means is that one is associated with the motion of charged particles, right? And that current is referred to as a what? Well, yes, both are electrical currents. Mike, I think you are electrical engineer, right? No, who is electrical engineer here? Oh, yeah, I mean, when I ask, nobody is. Yeah. No. This is a third thing. Yeah, we can say that electric current is a phenomenon and electric current is a quantity, physical quantity. However, for a phenomenon, we don't have a formula. Only physical quantities have formulas, and only physical quantities are involved in the formulas. Yeah, so now I recall, because I mean, I'm sorry about, but really to grade a test takes a lot of time. But I remember that somebody in the Lenz equation said that S and S prime, or P and Q, that they are object and image. Yeah, so 1 over object plus 1 over image is 1 over focal length. Obviously, it doesn't make sense. We don't know how to find an inverse of an object. We have to, well, inverse of a distance would be fine. However, it was inverse of position. All right, what is the other I then? Dan, how about you? I mean the first I, yeah, let's say the first one, the one which is associated with the motion of charged particles. This physical quantity is electrical current. What is the missing word, which we often skip? Teja. Conduction. So this is conduction current, electric conduction current. What's the other one? And what was this? What is this current associated with? It is not associated with the motion of charged particles. Do you remember where this type of current flows? Yeah, because conduction current, for example, flows in a wire, right? If we in a circuit, if we have wire connecting elements, current flows in the wire. But there can be a place in a circuit when this current flows and it is not associated with the motion of charged particles. And I think you use already this word today. Can you say the word again? Where this type of current flows? What word did he say today? Capacitor, correct. Yeah, between the plates of the capacitor, we don't have charge moving. However, what happens when we charge or discharge the capacitor? Something happens in this capacitor. What? The electric field changes. Well, if the electric field changes, if I consider a surface across around that plate, I can recognize that the flux of electric field changes. It means that this current flows. What do we call this current? Oscar, did you get it? Starts with D. Yeah? Displacement current, correct. So this is, here we have the definition of displacement current. We have two definitions because these are two different quantities. This quantity describes motion of charged particles. This quantity describes changes in the electric field. How about that one? What's that one? Because I mean, this is a formula which we often used. What was this about? Mike? Correct. That one was for capacitor. Yes, so there is a difference in Q. Over here we have small q, over here we have capital Q. What is Q in both cases? Electric charge. All right. Now, why in one case we have capital Q and in the other we have small q? Teja, could you quickly do that so that we can leave the room?
Capital Q is for capacitor.
The capital Q is the charge on the capacitor. So, very good. So, Teja, could you read this derivative? So, this derivative represents what? The rate of change of the charge on the capacitor, correct. So it's the rate at which capacitor is being charged or discharged. How about that one? Oh, this is not a rate of change anymore. Yes? What was this dq over there, dq over dt? It was also the rate, but not of change. A rate of flow, correct. So this was rate at which charge was transferred through a surface. Remember that current is always associated with the surface. When we say current in a wire, we really don't mean current in the wire. We mean what, Ian? Current through a surface. What surface? Yes, cross-sectional surface of the wire, correct. Isn't it exciting to have a review? I mean, I know that our juggling is still a little bit sloppy, but we are getting there, and in the next classes probably, I mean, not tomorrow. Tomorrow we are going to juggle too, so we are going to make reviews of the formulas. And thank you very much. This will be all for today.